you know, when you solve Einstein field equations with the torque, people could say, well, okay, but you're adding torque, but what's creating the torque? And the answer for that is that those equations are based on Laplace-Poisson earlier equation, which are equations of density. And what that means is that the density of the field is what drives the space-time torque. That is, because there's different vacuum density from infinitely dense to infinitely undense, but never absolute vacuum, then just like high pressure, low pressures of gases in our atmosphere generates a hurricane, then you get a galaxy, or you get a star, or you get a planet, or so on, because there's density change that drives the whole system from infinitely dense to vacuum state, you know, in the extremely large. So you can see that these change that occurs in supernovae dynamics, they resemble very much what we just visualized with the little string ray machine. Here you get the same kind of dynamics. So here you get a hurricane, right? This is off the coast of Florida. And here you get a galaxy. Completely different scales, same dynamics. What do you find in the center of a hurricane? The eye of the hurricane, which is stillness, which is the vacuum state geometry, which is the place where it gets the coldest. And then at the center of the galaxy, you find the black hole, where past the event horizon, all thermodynamics are absorbed and so on, and you leave behind vacuum state geometry. So same dynamics at completely different scale should tell you something about that force and about these change of density. Imagine the change of density between galaxies, which in fact only brings molecules centimeters apart. And then the density inside a galaxy, which is much higher. And then the density inside the solar system, which is much higher. And then the density on the surface of the sun, which is much higher. And then again and again and again, because things are not homogeneous. They have different viscosities and different densities, which drives the space-time torque. This is a picture that was taken at the Sydney University of the energy levels, the energy dynamics around carbon atoms, molecules. And so here we see the same vorticular, you know, dynamics of the space-time torque, according to my views. And we'll get into very high scales level. This is surveys that were done of superclusters of galaxies that's extremely large. And when they looked that far, they expected that things would be quite chaotic and not organized and so on. And instead they found the exact contrary. These very large scale structure organizes in octahedrons and tetrahedrons array way out there. And these papers are actually published in literature and called fractal or egg carton universe and stuff like that. That's what they're seeing out there. And basically, it's just like this. If you got your nose in the rug, if you got your nose in a Persian rug, there's no way you're going to think that there's a pattern to it. You're just going to think it's all chaotic. But if you get far enough from it, if you change your scale relationship, all of a sudden you start to see the pattern appear. And that is what I believe we're starting to see, is the actual structure of space-time and how it organized matter. Even the table of elements. That was extremely large. Now we're going to much smaller atomic structures. Even the table of elements has been solved by Dr. Moon at the Chicago University to be able to solve for all the protons, neutrons interaction using the 5 Platonic solids, very specific geometry, and then even all of the electron interactions using the Archimedean solids and the vector equilibrium and so on. This is Dr. Moon, the late Dr. Moon. Oh, well, that's one of the statements he did at the end of his life. We are entitled to seek geometry, to seek a geometry of space, or in other words, we are no longer able to talk about empty space. That is, from his findings, he figured that there's got to be some geometry in space that's dictating those particle interactions. If you go even smaller, or you're getting to the electron clouds and the orbitals, you find that these probability orbitals match very specific geometries that have to do with tetrahedron and octahedrons. The group theoretical models that predict subatomic particles are based on geometry. I mean, they emerged from crystallography. That's where these models came from, except that typically physicists ignore the geometry. They say, no, that's just a way to solve the equation. I believe that the equation is solvable in geometry because the geometry is fundamental to these particles' interaction. You have to have that geometry to be able to solve it. And, you know, we find that these interacting, group theoretical models match the isotropic vector metric, the vector equilibrium, and so on. So now we're at the extremely, extremely small.